Hello, with a little bit preparation from the probability exercise from last week, we officially start the first chapter. So the first chapter is claim frequency. In other words, in the first chapter, we study the number of claims. So we study how to model the number of claims. Okay, in most applications, probably we will focus on a pool of policies. For a pool of policies. That means we look at this problem from the angle of insurance companies, right? Because usually insurance companies do not care about a single policy, but rather consider all the policies pooled together. But of course, from time to time, we may also consider a particular policy or a particular set of policies. Like maybe they are a few very, very bad drivers who tend to incur a lot of claims over the insured period. So it's probably of interest to the companies to look into what's going on with those customers, right? But anyway, we will know the subject of study, and what we are trying to consider is the number of claims for the subjects. Okay. So here is a quick slide of references. The third textbook is our required textbook. So most of the slides, from here are taken or modified from Cai's textbook. So it's a good idea to read through his book. I would say it's an excellent textbook. The basic mathematics is probability. So if you have, say, a little issue from the exercise, it may be a good idea to take a look at the second book. Okay, so that is the book from Sheldon Rose. He's a very famous person in probability and has written many outstanding textbooks. Book 2 is one of them. And then, actually, there are quite a few of you are PhD students. Okay. And the book 1 is for you. If you are PhD in mathematics, in statistics, or in actuarial science, it may be a good idea to actually study probability at a much higher level. That is book 1. Book 1 is for PhD students. Okay, it's as the title says, it's probability and measure. So book 1 teaches you probability from a measurable sense of understanding. So it's the theoretical side of probability, which sometimes people call measure theory. Okay, it's a very difficult book, and you will need to spend a lot of time on it. Okay. Section 1, I call it preliminaries in probability, which is not exactly accurate because definitely they are not exactly preliminaries for this course. It's actually much more advanced. So if you have issue understanding the advanced materials from this section, it's probably okay. Give yourself some time to digest, and if in the end things still don't look right to you, it's okay to go on, because we really don't need everything from section 1. It's just me trying to be slightly more complete, more accurate, in terms of probability. So I give you an overview at a little higher level. So let's start with the first item, okay, which we call sample space. A random phenomenon is a situation in which we know what outcomes could happen, okay, but we don't know which particular outcome will happen. So let's say in this course, right? Wow, you will, in the end, you will get a grade, okay? It ranges from A plus, A minus, all the way down to fail, okay? So it's that all of you know, right? Which means you already know what outcomes could happen, okay? But at this time, you don't know which grade you will be getting, right? So you don't know the final result, okay, yet, but you know the final result will be taken from one of those categories, okay? Here I say, the number of outcomes next year is random. You know it's a number, right? Let's say 1, 2, 3, all the way. Well, you can even go to infinity, right? So we have the set of all possibilities. We just don't know which one will happen. That's why we call those a random phenomenon. Of course, sometimes we also consider a constant case as a trivial random case. For example, like say today is Tuesday. You know exactly tomorrow will be Wednesday, right? So there is no randomness in that. But sometimes we also treat this as a trivial example, right? In this case, we know exactly, what will happen. Here, how do we define? A combination of outcomes, gives you an event. So here, it's really, really a broad definition, right? A combination. I didn't specify how you combine them. Right? It can be anything. Right? Does not even need to be that belong to the same category. Right? We can mix name, age, gender, into the same combination. Right? So it's just anything you want to put together. It's an event. Okay. For instance, we can define the event of pass to be your grade or to be your scores between 60 and 100, right? So if the aggregate score of your of you from this course is greater than 60 points, you will pass. So that's how we define an event, for instance. And usually we use capital letters to denote event, like A, B, C, D. So now we have the first formal definition. The collection of all possible scenarios is called the sample space. And we use omega. Okay, so this is big omega. So it's omega. Okay, we use small omega. This is small omega to denote a specific scenario. So let's look at an example. Okay, I like to use examples to illustrate some abstract definitions. In a gamble, one tosses a coin twice. Okay, assuming for the coin there are two faces, right, head and tail. What is the sample space of the tossing result? So you have two tossing, so it can be head, can be head, tail, can be tail, head, can be tail, tail, right? So like I assume, it's whenever you toss a coin, you get either a head or tail, right? And so for each tossing, there are two results. Okay, you toss the coin twice, so 2 times 2, you got 4 complete exhaustion of the scenarios. So this is the sample space. So this is the sample space for this example. Okay, and of course, you can think many cases. Like for this example, your sample case could be 0, which means nothing happens. Can be 1 claim, can be 2 claim, all the way to infinity. Right? Sometimes you can cap this at certain number. Let's say if you look at a particular policy, maybe it's safe to discuss up to 10, right? Because in the US, the coverage of one auto policy is usually for 6 months, and it's probably reasonable to assume that nobody will incur 10 claims within 6 months, right? But you can put it as large as you want, right? So that's the sample space. So basically, sample space lists all the possible scenarios of the random subject you are trying to study. Okay, so that is the sample space. Then sample space, it's a set. So it makes sense to talk about some operations on sets. Okay, in definition 2, we have 1, 2, 3. 3 different type of operations. The first one is complement. So basically, complement is the remaining of the subject. So this is called a Venn graph. You draw a square or rectangle to denote the sample space. Okay, let me get a different color. So let's draw a circle to denote this set. So this is my set A. So everything inside is set A. So now the complement is nothing but the outside part. So complement will be, so these will be the complement. So basically it's the sample space minus ZA, right? So this is a complement, okay? Union, so let's draw union. Again, it's a rectangle to denote the full sample space. And I have one set A here. I have another set B, okay? And the A union B is nothing but everything. So in some sense, A union B, it's somehow close to our idea of addition, right? You add two sets together, but remember, here is the common part. Common part is actually the final operation. So this part, so let me just fill this part. This part is A intersect B. So when you do the union, you actually have A intersect B from both A and B, right? Because that is the common part. And when you do the union, you only count this common portion once, okay? So that's why we have, remember in the exercise, we have this famous addition rule. So by the way, when we draw the Venn graph, you think probability as the area of, let's say here, if you want to talk about probability of A, it's just the area of this circle. So that's why when we calculate the probability of a union, it's A plus B minus the intersection part, because A, when you calculate probability of A, you count the common part once. When you calculate probability B, you count this part twice. So you overcount once. That's why you need to subtract back, the joint part. So that's something all of you should know, obviously. Okay, the next part is unusual for this level of course or for any actuarial science, because usually you don't need to talk about sigma field or sigma algebra. This is a collection of subsets, okay? Subsets of omega, okay? So what is subset? Subset is just that you take some part of omega and form a new set, right? So in the previous example, we have in the coin example, our omega has 4 results. You can take any one that is a subset. You can take any 2 is a subset. Any 3 is a subset. All of them is also a subset. Okay. Now, when we get or when we're trying to form a sigma field, it is collection of subsets. So it's actually set of sets. Okay. For instance, this is a possible collection, right? Because this is a subset of omega. So this is the notation for subset. The second one is it's also a subset of omega. I can collect them together. So here, when I collect, I do not collect each element, okay? So I may collect some sets or some collection of elements, because this is an element in omega. This is also an element in omega, and I put it in a set notation. So so which means I treat them as a set instead of an element. So that is some, delicate difference. Okay. So once I collect them, I can try to get a new formation. Okay. So this somehow, we call it a sigma field or sigma algebra. It must satisfy 3 conditions. The first condition is it should contain an empty set. Okay. Here I have a remark, empty set is not the same as a set with 0. This is not empty. It has an element of 0. It's not empty. So what is empty set? Is this? Nothing. It includes nothing. Okay, so that's empty set. So in the second property, so if A is in this sigma field, F, its complement must be also in this collection. In the third property, usually, we when we have, this is called I from 1 to infinity. When we have AI in F, the union of it should also be in F. Okay, of course, because the complement is also in F, you can also define this as intersection if you want. Must be also in F. Okay, so those two are equivalent. By the way, you can have a rough idea of why we need those three properties, right? Because if empty is in F and the complement is also in F, we know it includes the sample space, okay? And given all those properties, we can do all the operations we just defined. They are closed. Closed means when you do this operation, the result you get is still in this collection. That is great, right? That is something similar to our idea of real numbers, right? So we begin with positive, right? Begin with positive integers, right? Like the 1, 2, 3 all the way, right? And when we have 1 minus 2, which is negative, right? Which is negative not in the set of positive numbers, right? So we generate to all natural numbers, right? So, and then we have 1 over 2, which is not an integer. So we need to generate to all rational numbers, right? And still, we can, when we take some operation like take a square root, okay, you get a non-rational. So you finally generate to all real numbers. The same idea is here, right? So why do we need sigma field? Because sometimes when we do set operations, we end up with not in this collection, which is really, really not good. So that's why we need to add those properties so that you can do whatever you want, and still you end up in the same collection, okay? So that's the whole point of defining sigma field. The last element is probability measure. Okay, in the general level, you define probability measure as a function. Okay, and this function maps from sigma field. Okay, in your first probability, you define probability from sample space to 0, 1, right? Now you define probability from sigma field to 0, 1, okay? And if you study something even more general, it's from sigma field to real numbers, right? The probability does not need to be between 0 and 1. I mean, measure does not need to be between 0 and 1. And sometimes you can even generalize to have a signed measure, right? It does not even need to be positive. It can be negative. So here we have two conditions. So first, the probability of the sample space is 1. And if you have disjoint sets, disjoint meaning AI intersect AJ is empty if I is not equal to J, okay? And if you have disjoint, the probability of the union is the summation of all probabilities. Well, this makes sense, right? At least for two sets. They don't have any union. So apply our addition rule. The union is just the PA1 plus PA2, right? Because there is no intersection, okay? So this generalized to infinity. So this is called countably many, right? So the triplet is finally the so-called probability space. So this is usually the first abstract concept you get into when you study measure level probability, okay? Some may wonder, why do we need to define probability from sigma field to 0, 1 instead of sample space? The answer is for us, it really doesn't matter. It's the same. Right? For us, it's the same, okay? But of course, there are cases you don't just define, from the sample space because you don't even know how to define. For instance, if you consider continuous random variable, Okay, so let's say I have a random variable from 0, 1. So it's defined from 0, 1. So the sample space is continuous. Okay, how do I define it? Right, I can take a point. Right, a point, gives me 0. Right, we know for a continuous random variable, the density is 0. It's not defined. You must get an interval to talk about the definition, right? So when you have a continuous, you must have an interval to talk about the definition, right? And the interval, what is the interval? Interval is a subset of this sample space, right? So technically speaking, you are defining probability measure for a set, right? A set here is from A to B, right? So this is a subset, right? Of course, A and B should be between 0 and 1, and A should be less or equal to B. So technically speaking, it's a subset, right? So that's why, but for discrete, it really doesn't matter. And for continuous, we also don't specifically talk about it. We simply assume we know the CDF or we know the PDF, right? So that's we taking things from an easy point of view, right? We are not trying to do everything with the full mathematical rigor. So for us, especially for discrete case, it is really enough to simply define probability for each element or for each scenario. All we need is to make sure each PI is between 0 and 1, and when you sum up, you get 1. That's all you need. So this condition is the same as property 1, okay? So I give you a quick example. In this example, we already mentioned the sample space. I give you two possibilities of sigma fields. The first one is a trivial one. It includes only two members. The first one is empty set. The second one is the sample space. So I ask you to verify this is indeed a sigma field, which means it satisfies the three properties, okay? The second one is another somehow a trivial case, that is, it includes everything. So that's we call 2 to sigma, 2 to omega. So that's considered includes everything. Okay. So I ask you to list all everything. For instance, so which means here omega has 4 elements, right? 2 to the 4. Okay. So which means it has actually 16 members in this. Not omega. So it's a sigma field. So for instance, you can start with empty set, which means it includes nothing. And then we can talk about include one set, one element. So there are 4 options. Okay. Next, we talk about the set with 2 elements, HH, HT, etc. Right. So here, how many do you have? Right. It's a combination number, right? So you can exhaust this. Okay. The reason why it is 2 to omega is because of the combination, right? So first it's C40 plus C41 goes all the way to C44, right? That's exactly how you get the combination number, okay? Continuous sample space, example 3 is too difficult. I just put it. If you're interested, you can take a look. It's definitely way beyond this course. So random variable, okay. Random variable is another important concept in this course, okay. Here I define it as a function. Real random variable is indeed a function, okay. So it's except it's slightly different from our usual sense of function, because when we talk about a function, so let's say I have a function g. In your first year calculus, is usually from real number to real number, right? For instance, let's say g of x is x squared. So if you know a number x, you know g, or you can put it as a y, okay? So it's a mapping from a number to another number. But when you study random variable, it's not from a number to a number, right? It's from a random scenario to a number, right? So your x, your small x, is random. Is the random scenario, right? It's one of the elements in the sample space omega. Like in the previous example, it could be HH, because there are 4 elements, right? One of them will happen. So you are trying to list all the possible outcomes when a certain result happens. Like for instance, you can define if you get one head, you collect $5. If you get two heads, you collect $10. If you don't see any head, you get zero. Right. So in this case, what do we have? HH is 10. HT equals XTH is 5. X tail is 0, right? So we just define a random variable. It maps from all possible scenarios. In this case, there are 4 to a number. So this is the definition of random variable. And often I will just use this short notation, RV, to denote random variable. Okay, so it's nothing but a real function, except the domain is from somehow more abstract space instead of the real space. Okay. So of course I have one more example, but there it's actually simple. Okay. So then we define, once we have a random variable and when we have this probability space, we can define the cumulative distribution function. Okay. I use CDF. The textbook actually use DF, which is slightly less common than CDF. Okay, CDF is more common, so we call it CDF. Here I use lower letter. Some people may use capitalized, so the same thing. So CDF of a random variable is nothing but the probability of it less than or equal to the given level. So the CDF is a function. Okay, this is a standard function, means it maps from real number to 0, 1, because it's probability, right? So it's a probability of something. It's always between 0 and 1. And here your X is real number because we talk about the possible scenarios for the random variable. So we do not care the scenario part. What we care about is the final end of this result. So we want the random variable to be less than or equal to some number. So here small x is a number. It's no longer omega. Okay, but of course, when we calculate the probability, we need to go back, right? We need to go back to figure out what omegas will make this x less than the given small x. Okay, so that's the definition of CDF. I'm pretty sure you all know the definition of CDF. Here we have a quick theorem. It's not that important, but let's quickly mention it. Okay, a function is a CDF if and only if this function is non-decreasing and right continuous. Non-decreasing because probability it's always between 0 and 1, right? So when x increases, the set will not decrease. So that's why it's non-decreasing. And the right continuous is because when we define probability, it's x less than or equal to. If it's less than, then it's left continuous, right? So here we take the right continuous part and has 2 conditions. Again, that's because the CDF is always between 0 and 1. So when x goes to negative infinity, you must get 0. When x goes to positive infinity, you must get 1. Of course, sometimes you go to 0 much, much faster. So let's say you have a positive random variable. Okay, then you have f0 is 0, right? Of course, when x goes to infinity, negative infinity is also 0 by the property of non-decreasing, right? So f negative infinity is less than f0 and it's also greater than 0, so it's 0, right? So in some cases, you have the random variable decreasing to 0 much faster. Here I have a quick graph of 2 possible distributions, which we will, of course, get to sometime later on. That's good enough for this video. In the next one, we will start learning more of the discrete random variables.